Okay. Hi, everyone. Good morning, good evening, good night. My name is David Kanter. I'm chair of the International Nitrogen Initiative and associate professor of environmental studies at NYU, New York University. It's my pleasure to welcome you to the third I&I webinar around the theme of halving nitrogen waste, with a focus today on green ammonia. This is an emerging, a fastly emerging technology, which could have very significant consequences and impacts on both the global nitrogen cycle as well as our capacity to produce energy potentially sustainably. And we felt as a scientific community and as the leading international network of scientists and stakeholders working on nitrogen that it was unavoidable to discuss this really important topic. And we're really excited today to have four great speakers with us. Trevor Brown from the Ammonia Energy Association, Matteo Bertagni from Princeton University, Sarah Garvey from the NICCEE Center, the Global Nitrogen, I'm not going to do the acronym right now, you will do the acronym, and Dr. Zhang as well, also from NICCEE, who will be joining the Q&A later on. So I will just I want to briefly introduce all of these speakers, and then the way that this webinar will run, as it has in the past, is we'll have each speaker speak for give a short presentation, and then we'll have some moderated questions from myself, and then we strongly encourage you. There should be a Q&A feature down in the Zoom, and our great operations manager Edin Thornton, who's here, who many of you know and have met in person, will be collating those questions and trying to make sense of it all for us. So in turn of who will be speaking, Trevor Brown is the executive director of the Ammonia Energy Association, which is a global trade association that promotes the responsible use of ammonia in a sustainable energy economy. This association's mission encompasses both the decarbonization of ammonia for existing applications, as well as the adoption of low carbon ammonia in new applications, including direct use as a fuel and indirect use as a hydrogen carrier. Matteo Bertagni studies the feedbacks between hydrological and biogeochemical cycles, with a particular focus on soil and the environment. Looks at the efficiency of natural climate solutions and the capacity of soil bacteria to consume atmospheric hydrogen. He's currently a postdoctoral research fellow at Princeton University, and got his PhD in the University of Torino, and very excited to have him here. Sarah Garvey is the program manager, now I have the full acronym spelled out, the Global Nitrogen Innovation Center for Clean Energy and the Environment, which is NICCEE, great acronym. Received her BA from the University of Pennsylvania in 2016 and a PhD at Boston University in 2023. And finally, Zhang, who I've known for a long time, did her undergraduate at Peking and her master's at Peking University, PhD from Yale, and is one of the leading scientists on nitrogen and is the project director of this new NICCEE Center with its focus on green ammonia. So I'm really excited with the panel that we have today. And with that said, I will stop talking and hand over the microphone to our first speaker, Trevor Brown. So Trevor, thank you so much, and you have the floor.
Well, thank you, David, very much. And it's an honor to be here with these other speakers. I'm going to share a quick slide deck that I hope is now visible. And just do a really quick introduction. This is a huge topic. It gets very complex the moment you start digging into different areas of it, which is why there are so many PhDs in my other panelists. And so I want to just introduce the concept that the Ammonia Energy Association is promoting, which is this dual concept that we need to decarbonize ammonia. And if we can decarbonize ammonia, then we've got a carbon-free molecule that can have a useful role in energy systems. So the Ammonia Energy Association, I'm the executive director here. We've been around for 20 years. We relaunched as a trade association 5 years ago when this became something that moved out of the academic R&D space into a space of industrial implementation. And we've in the last few years gone beyond purely conceptual ideas and feasibility studies into very large scale implementation. We've got 1 million ton per year green ammonia plant under construction in Saudi Arabia. We've got green ammonia being produced in the US, in Europe, being turned into low carbon fertilizers, being turned into low carbon products by companies like Heineken. And so these supply chains have started to actually implement the concepts that I'm going to talk through. So for me, this is very exciting. We've been spending a long time talking about the concept, the potential, the feasibility of decarbonizing the sector. And now we're doing the implementation. So here's just a really quick introduction to the concepts. As background, the association itself, we are a group of more than 260 different companies from both around the world. So we do a lot of work connecting different regions, but also across the value chain. So we do a lot of work trying to connect the people who think about fertilizers with the people who think about maritime fuels, with the people who are electric utilities. And traditionally, these companies don't talk to each other, haven't had a need to. But as we look towards the sort of energy systems we'll have in 2050, they need to be working together. They need to be closely correlated and to deliver the kind of investments in both production and use and infrastructure. Everybody needs to be pulling together and connecting that supply chain to de-risk that transition. So the concepts that we begin with at the Ammonia Energy Association is just to start with. We know, I think in this group, we know quite a lot about ammonia already. It is a natural substance, and we've been mass producing it for 100 years. It is a chemical that goes into every sector of society, from pharmaceuticals to explosives to refrigeration. My dad was a refrigeration engineer, so my childhood was going around ice rinks on the weekend, touring his ammonia installations in Scotland. It's used to disinfect drinking water, so it's in cities all over the world as a pure anhydrous ammonia being stored, being used all over the world. But we make it from fossil fuels, which is a bit sticky in this day and age because we've got an emissions problem. And we're focused to start with on greenhouse gas emissions. And if we think about ammonia, we're talking about 450 megatons of carbon dioxide per year, just in the production of this one chemical. So that's roughly 1% of global emissions. If it were a country, it would be somewhere between Turkey and Mexico. So there's a serious challenge to decarbonize something of that scale. And we have to stand up and meet that challenge. So, we've got a commitment to achieving net zero by 2050. This is set out in the Paris Agreement. You've got countries and companies around the world committing to this target. For ammonia, there's a unique aspect to this, which is not only that we need to decarbonize what we're currently doing, but to achieve net zero by 2050, we're going to be doubling, tripling, quadrupling. I'm not sure how much more ammonia we're going to need, but to provide additional molecules for that low carbon economy. So simultaneously decarbonizing and increasing the market volumes in order that we can achieve net zero by 2050. And so that's quite a complex prospect. There's a lot of people who will be really happy to tell you that making green ammonia for fuel use is a waste of energy. And in many cases, they're absolutely right. There's lots of uses of fuels that you can think of that are very wasteful. But there are other uses for molecules in a low carbon economy where you simply you have to have the molecules. You can't plug in a container ship. It's not feasible. You need a molecule on that ship that's not going to create greenhouse gases. And so there is a role for low carbon molecules in society. Identifying the best roles isn't going to be a one-shot solution. There's going to be different places, different sectors where different solutions make more sense or make less sense. And so rather than thinking about silver bullets and the optimal uses, we need to look at individual business cases, localized solutions, and where and what ammonia can actually be used for best optimal use. And so some of the uses that we're looking at and that we're seeing being deployed now across society, obviously there's the simple concept of power generation. You can burn ammonia in internal combustion engine, in a turbine, in a fuel cell. There's many ways to change the energy contained in that molecule into power. Now, whether that's in an electric grid or whether it's in an off-grid situation, whether it's for peaking purposes or whether it's a seasonal baseload kind of profile, those are very regionalized local questions that will be answered in different ways in different sectors of the economy. The US electric grid is going to have a very different approach to low carbon molecules relative to the Japanese electric grid. We've got a big problem to solve around industrial heat. Very large segments like steel, cement, glass that use tremendous quantities of fossil fuels to make heat. That's going to be quite difficult to electrify because quite often those are places that don't have a huge amount of electricity. And so finding the role for low carbon molecules in those sectors is going to be useful. I think the heavy duty transportation is a well understood segment, and we've got a lot of discussion around different molecules for that. I think maritime shipping is something that people are becoming more familiar with, the concept of using ammonia or methanol or biofuels or eLNG. There's a lot of different options, and most likely all of them will be in use over the coming decades. Another role for ammonia is in that desire for a hydrogen economy. If we look, for example, at Europe or South Korea, we have very strong targets for the use of hydrogen in the economy, but not enough domestic hydrogen production. And that means you're going to be importing hydrogen, but hydrogen is quite difficult to import. Therefore, you look to derivative molecules that you can import, and then you might think you want to crack that ammonia or that methanol back into hydrogen, or you might want to use that ammonia directly as a fuel. I think there's still a lot of work being done on exactly what the end molecule in those systems might look like. And finally, and this is sort of beyond where people are thinking today, because today what we really need to do is build more wind turbines and more solar panels. But ultimately, in 2050, we hope not to have a whole bunch of heavy fuel oil and coal and natural gas in the energy system. And so you'd think that you'd want your strategic stockpiles of fuel reserves not to be crude oil. Which begs the question, what would the strategic fuel reserve be? And at that point, you look to the role of molecules in the economy. And I think that ammonia certainly is going to be one of those strategic energy reserve molecules that provide resiliency in the economy. Obviously, all this has to be managed safely. And it has to be managed in a way that works both for human health and safety and also environmental safety. So these two things are absolutely critical starting points in these conversations. But as we know, we use ammonia. We make 180 million tons of it every year. We ship it around the world, and we have people on the last mile delivery, using ammonia on a daily basis, fully trained with ammonia with a well-established set of codes and regulations and training, first responders knowledge. Ammonia is not a new molecule in these situations. It might be new, however, for some of these applications I've been talking about. And so the critical concept here is that we need to be managing the knowledge transfer from the existing industries into the future industries to make sure that, first of all, we're not starting from a blank sheet of paper. We already know best practices. We know what we need to do to manage the hazards of ammonia safely, but we need to make sure that we're transferring that knowledge from the existing sectors to the new ones. So this is a slide that I find quite useful. This gives you a sense of some of the numbers that may or may not be market volumes in, for example, 2050, with roughly 185 million tons per year today, moving to somewhere between 500 to 1,000 million tons in the 2050 timescale, split between existing applications, shipping fuel, power generation, and the role of ammonia as a hydrogen carrier. For that to be feasible, obviously, we need to be not using conventional ammonia, or as we have it in this picture, the gray ammonia. That needs to be replaced by green and blue and other low emission technologies. A lot of that product is under development. This is a chart that shows you how much ammonia capacity, how much low emission ammonia capacity is already under development. So roughly 300 million tons of ammonia capacity is under development around the world. Excuse me. Of this, we would only expect about 22.5 million tons to be operational this decade. A lot of this capacity is, I don't want to say speculative, but it's not developed yet. We've got very few investment decisions. Very little of it is under construction. The purpose of sharing this slide is really to demonstrate there's nothing stopping us from building clean ammonia plants. There's no critical materials that are missing. There's no shortage of air or of water. What there is a shortage of is clear demand. So we're talking about climate solutions that are going to be more expensive than business as usual. And the business case is still struggling to really demonstrate enough confidence that, for example, container shipping fleets are pre-ordering volumes of ammonia fuel for the 2030s. That's not happening. And that makes the business case of going down and building an ammonia plant in 2024 quite difficult. So a lot of work is going on right now on that corner of connecting the supply chains so that producers and project developers can decarbonize their ammonia capacities, providing the low emission ammonia to the market in the future. Bringing it back to the conversation we're having today about reducing nitrogen waste. Everything I've said so far is focused on a carbon problem. And it's absolutely critical that we're not creating a nitrogen problem while we do that. So we need to be doing joined up thinking. And I'm very glad to be here today having this conversation on the impacts that potential ammonia, low emission ammonia economy would have on nitrogen cycles. We're going to hear from Matteo in a moment, and I've borrowed one of his charts here that sort of, for me, summarizes the big picture. You know, on the one hand, you've got natural reactive nitrogen cycles, then you've got anthropogenic nitrogen, and then you've got the potential impacts of the ammonia energy economy. From my perspective, I think that the ammonia economy has some challenges that are existential that will need to be solved prior to ammonia causing a significant nitrogen problem. And that's very simply human health and safety. The danger limits of ammonia emissions on human health and safety are so low, down to 5 ppm, you're smelling it and know you need to get out of the room. And the impacts of ammonia are so dangerous to human health and safety that I truly believe it would, from a human health and safety perspective, it will not be permissible to have significant leakage rates in an ammonia system. That's the starting point. Where we build that needs to be demonstrating that we can achieve it. It's one thing to say we've got a good safety record, that ammonia isn't being, we're shipping 20 million tons of ammonia around the world every year, and it's not spilling, and it's not causing great environmental catastrophes. And we do manage it well, but we need to ensure that safety record can be put forward in the expansion of the industry and in the use of it in new applications. And that is a tremendous challenge. It needs to be handled very, very well. And so we could dig down into lots of these different areas. I've tried to do a very sort of quick overview of the ammonia energy economy concept. But David, back to you.
That was great. Thank you so much, Trevor. Thank you for giving us both an introduction to the broader ammonia energy industry, its potential. A lot of that data, I think I'm speaking from an academic perspective, it's, that kind of data of projected capacity and things like that is something that we don't get to see every day. So it's very helpful to have that context and have, it's one thing to kind of theorize about what ammonia could be in both the opportunities and challenges associated with it. So to actually see plant capacity under development and to see exactly how the industry is thinking about some of these challenges is really, really helpful and fascinating. So thank you very much, Trevor, and I'm sure there'll be a lot of questions. I know I have some. Next up, we have Dr. Bertagni, Dr. Matteo Bertagni, who wrote this paper published in the Proceedings of the National Academy of Science, along with several others published last year, showing the potential risks associated with ammonia energy. And so, Matteo, very happy to have you here, and please, the floor is yours. And I believe you're still muted.
Well, thank you. Can you see the slides?
Perfect. Yes, we can. Perfect.
Okay, well, hello, everyone. Thank you, David, for the invitation, and thank you, Trevor, for setting the stage. And I agree, it was a great presentation. And what I'll do today is talk about a work that I've led in collaboration with many professors across departments at Princeton University, from combustion expert to environmental scientists to energy engineers and so on. And really the work is about minimizing the impacts of ammonia energy on the nitrogen cycle and climate. So I have a couple of slides of introduction about the ammonia energy, and I think just I'll follow up on what basically Trevor said. Okay. This is a scenario from the International Renewable Energy Agency for future hydrogen international trade, because there are international plans basically to produce hydrogen, especially when we're thinking about green hydrogen, where renewable resources are abundant. And so, for example, Middle East, North Africa, Australia, Latin America. And then part of this hydrogen will be exported to demand centers like Europe, Japan, Korea. But moving around hydrogen is very complicated, and I have another slide about it. And so really the use of ammonia could be critical for hydrogen transport. So just a couple of words on why hydrogen is difficult to transport. Well, hydrogen has these very high gravimetric energy densities, so a lot of energy per unit of mass, but very low volumetric energy density. And so basically it requires a lot of volume to be stored and transferred. So the potential solutions, if one doesn't want to change the molecule and just keep the hydrogen, are to either compress hydrogen to very high pressures or liquefy it to very low temperature. We're talking about plus 20 Kelvin. These operations are very energetically demanding, prone to hydrogen leakages with risks for safety, economic loss, and even indirect greenhouse gas effect by hydrogen. And so it could be really convenient to transform the hydrogen into the ammonia through the Haber-Bosch process. It is a very well-known industrial process done by basically a century. And ammonia could be stored in much more reasonable condition, for example, as a liquid phase at -33 Celsius. One thing I'll point out here is that you see how ammonia is on the other hand of the spectrum compared to hydrogen, in the sense that there's a very low gravimetric energy density. So basically what it means is that you need a lot of nitrogen to have a decent amount of energy. So then this ammonia could be transported and then used into the energy sector in various sectors that Trevor mentioned before. And there are two potential uses that are not necessarily mutually exclusive, but I keep them as such for the moment. One is to crack the ammonia molecule back to hydrogen and then use hydrogen. And the other option is to directly burn the ammonia. From a stoichiometric point of view, this releases N2 and water. So basically, if we look at the cycle for nitrogen, we start from N2 from the air, and we end up with N2 from the air. But this is sort of like the theoretical closed cycle in which all of the nitrogen, there is 100% efficiency, is released back as N2. It's likely that there will be some inefficiency, losses, leakages, and so part of this cycle will be open. And so the question is, well, is there a risk of introducing additional disturbances to the nitrogen cycle? And what are the potential environmental climatic consequences? And I think this possibly is the most important one. Can we identify critical issues in advance to address them proactively? Okay. I'm an environmental engineer, and so the environmental aspects when we are planning low carbon solutions since the beginning, to me, is very important. And the results I'm going to present from now on are you can find them in the paper that has been published last year on PNAS. So I'll start just by showing schematic of the ammonia value chain so that we're all on the same page. Basically, the idea is to start from a primary energy input. Currently, most of ammonia is produced from fossil fuels, is gray ammonia, but clearly the plan is to decarbonize this ammonia production with carbon capture and storage or renewable energy. So we track a flux of energy, we obtain hydrogen, and clearly we have some loss of efficiency for hydrogen production. Then we couple it with nitrogen, we have a small energy penalty, and then we either crack the ammonia to obtain hydrogen back. And here is the current problem of cracking, is that is an operation that is very costly, both from a money point of view, but also energy. So that eventually you end up with a very small percentage of the initial energy you started with, and with a very pricey hydrogen. Clearly, this could change in the future. So the alternative is to directly burn the ammonia. So in this picture, what are the potential concerns in terms of reactive nitrogen emissions? Well, one is about leakages. And this is an analysis that Professor Max Zondlo and his postdoc Zhang did, and shows that around the largest fertilizer production plant in the US, in Louisiana, if I remember correctly, there is a plume of ammonia that is emitted due to leakages. So we know there are some leakages. And then there is the huge challenge about combustion. Ammonia is not a great fuel. It doesn't have great combustion properties, and it has this problem that clearly the fuel itself is reactive nitrogen and tends to create a lot of other reactive nitrogen species in addition to the potential unburnt ammonia. We're talking about NOx and N2O, and I'll talk about these more in detail. So now I just want to give a quantitative perspective. Okay? So these are the current emissions of reactive nitrogen species for some selected countries and regions. And these emissions englobe emissions from agriculture, the industry, and energy sectors, okay, all together. Now I want to compare with potential emissions from ammonia energy, depending on clearly how much ammonia is used in the energy sector and what are the potential loss rates. So I'm considering 5% of energy demand of these regions to be covered by ammonia. Clearly, there is a high degree of subjectivity of this, but that's to say, not a negligible component of the energy sector is covered by ammonia. And with 0.5 ammonia losses, we have these red terms. Clearly, if we increase the percentage that could be released into the environment as reactive nitrogen species, we get to potentially very high fluxes. To me, the message here is that even small amount, relatively small amount of ammonia energy have the potential to release substantial amount of reactive nitrogens in the environment. And so clearly there is a crucial importance about mitigating these effects and reducing these leakage and loss rates at a minimum. Probably most of the audience is already familiar with the nitrogen cascade, but just to give a sense of what happens about reactive nitrogen emissions, if we track an ammonia molecule, ammonia is toxic. It can lead to particulate matter formation, so it contributes to air pollution. When it sticks to humidity, it gets into the aqueous phase, and through wet deposition, it falls into soil or water bodies, where it alters the chemical composition of the soil. And usually here, biotic processes in the soil transform it back to N2 and emit it back to the atmosphere. If we are unlucky, there is a small percentage of it that could contribute to secondary N2O emissions. And N2O is a very powerful greenhouse gas that is only depleted in the stratosphere by ultraviolet radiation and is responsible for stratospheric ozone loss. So let's look at the same sort of evaluation, but for global numbers. Again, let's assume that we want to cover 5% of current energy demand with ammonia. And a possible justification to this is most of net zero scenarios see a contribution of hydrogen to energy demand about 15% to reach net zero goals. And then International Renewable Energy Agency assumes that around a third of it will be transported. And so let's say this transport occurs to ammonia. So the amount of ammonia will be needed is around 1,600 megaton. So this is 10 times current production that we know mostly goes for the fertilizer production, also in other sectors, but more than 80% of it is for agricultural purposes. And if this ammonia had to be shipped, ammonia shipping capacity would need to increase by around 80 times. So we are talking, as Trevor said, about a new infrastructure that need to be developed in parallel with potential increase in demand side. And now with these numbers, I'll show the picture that Trevor showed before. Going a little bit more in detail, this is the global perturbation of the nitrogen cycle, or global fluxes of nitrogen. So these are natural processes that fix nitrogen. These are the anthropogenic one, where we have the biggest term is the fertilizer industry. And now I'm considering the ammonia economy. So here we have that around 1,300 megaton of nitrogen should be fixed for ammonia production, right? But clearly this is 100%. The advantage of using ammonia into the energy sector, and really this is the huge difference compared to ammonia for agriculture, is that most of this nitrogen will go back to the environment directly as N2, right? And not released in reactive nitrogen compounds, but a part of it will. And so depending on the loss rates, we could have a really non-negligible term. Just to give you a reference, this dashed line without a label is actually the proposed safe planetary boundary for nitrogen. Now, a couple of more words on the issues of N2O. N2O is the so-called laughing gas because it's used in parties since the 18th centuries as a drug. Apparently, it gives a euphoria state. When we're talking about ammonia combustion, there are many reaction pathways that can produce N2O. But it's a challenge because it's a kinetic problem. What does it mean? Well, that if one allows to the combustion of ammonia to proceed until the end, then the amount of N2O that should be produced will be very low. But if the combustion is incomplete or there are some inefficiency due to several reasons, there could be N2O formation and emission. And this is a similar problem in a sense to carbon monoxide for combustion of hydrocarbons. Really, in worse conditions, there could be a selectivity of ammonia to N2O that is very high as 50%. Now, why is this a potential big problem? Because N2O is a powerful greenhouse gas, around 300 times more powerful than CO2 on a mass basis in absorbing infrared radiation. And as I said before, it also leads to stratospheric ozone depletion. So, it's actually the largest contributor to stratospheric ozone depletion in the atmosphere right now, basically since the Montreal Protocol has decreased emissions of other more powerful gases. So when we're talking about ammonia energy and N2O in general for climate change mitigation, really nothing to laugh about. And I'm going to show you just one more plot. This shows the greenhouse gas footprint of ammonia combustion for electric power compared to other energy sources. So these values from coal to wind that has the lowest CO2 equivalent impact, these numbers are taken from the IPCC. And then what I've done, I've taken numbers from the International Renewable Energy Agency for upstream emissions related to ammonia synthesis. And that's why these bars do not start from zero. And on top of this, I'm considering what happens if we have some N2O emissions, okay? And conversion rate of nitrogen into ammonia to N2O that is between 0 and 1%. So basically what we see here are several messages. The first one is if there is no N2O, there is a pretty wide variability of the ammonia greenhouse gas footprint, clearly depending on how ammonia is produced in the first place. And this is not surprising, but in the best condition, okay, it's not as good as possibly wind, nuclear, or geothermal or solar, but still better than biomass burning and definitely better than natural gas. But if there is some N2O conversion, it can become problematic. And really in worst case conditions, burning ammonia becomes worse than burning coal for climate. So we're not expecting these to sort of be a steady state combustion in which clearly 1% of the ammonia is not burned well and is released as N2O, but this could be transient effects that one wants to minimize to not lose the benefits in adopting ammonia for climate change mitigation in the first place. And so the take-home message here is that ammonia energy does require careful optimization through best use pathways, practices, technologies, and regulations. And I have one more slide on the open challenges from a technological regulations point of view. From a combustion side, I've said it already, basically, there are two main problems with ammonia burning. One is that it doesn't burn very well, and the other one is that it creates a lot of potential reactive nitrogen emissions. So there is a solution to one that actually makes the other problem worse, which is mixing ammonia with some hydrogen. Hydrogen can be obtained directly with the waste heat from the combustion process. And this clearly reduces the energy requirement for ammonia cracking. But this does tend to create more NOx, just because the temperature gets higher, because hydrogen is a great fuel, even too much. And so it does tend to form NOx. And differently than N2O, the NOx problem is an equilibrium problem. So even if ammonia combustion is allowed to finish and everything is done properly, there could be NOx. So basically, what combustion experts say is that we will not be able to burn ammonia with current technologies that are used for hydrocarbons, because the NOx emission could be too high, much higher than what most regulations worldwide allow. So the most promising probably way is to burn ammonia through a two-stage combustion. Basically, in the first stage, is rich in the fuel, and then there is some hydrogen ammonia left over that are burned in a lean condition in a second stage. And with these technologies, you could reach order 50 or 300 ppm of NOx. These are probably still too high. And just to make a precision, these numbers here, 300 ppm is around 0.2 or 0.3% of the ammonia, okay? Just to give a sense on the loss rates. And so it would be likely that we need some post-combustion treatment. And SCR, selective catalytic reduction, is probably the most obvious because there is already ammonia there, and one can use the ammonia to make it react over a catalyst with NOx and produce N2. That's the form of nitrogen we like to see back in the environment. From a cracking point of view, the biggest challenges are to making cracking technologies more accessible, both in terms of economic cost and energy intensity. From an environmental point of view, the advantage of cracking is that since it would be done mostly in the absence of oxygen, there should be very little NOx and N2O formation. Clearly, this requires that you have high conversion efficiency, because if you do leave some ammonia in the fuel and you burn it later with hydrogen, clearly you could still have the problem of NOx and N2O. Also, you might want a very high hydrogen purity for some application. In terms of regulations, I agree that regulations for NOx are quite common across the world, and they've been very efficient in the last decades to reduce NOx emissions. There are less regulations in terms of ammonia than N2O that are historically more of an agricultural problem. And so here there will be really a switch of paradigm in which these emissions are potentially coming at scale from the energy part too, if technologies and practices are not optimized. And also from a satellite point of view, detection is interesting because satellite analysis of ammonia plumes are very challenging. Ammonia stays in the atmosphere for only a few hours on average, and it's present in low concentration. And so there are technological limitations that are going to be partially solved when a new generation of satellites will be launched, probably in the first years of 2030. I want to just conclude by saying that yes, ammonia can help reduce our impact on the carbon cycle. It does have a potential to increase our impact on the nitrogen cycle. And I think this is a trade-off that can and must be minimized with coordinated effort from scientific community, clearly, continuing doing research in terms of highlighting potential criticalities. What are the solutions? What are the best use we could do of ammonia? Is cracking really better than combustion, and so on? And clearly this needs to involve the energy sector and governments. So with this, I thank you, and I really thank all the extended network of collaborators that participated into this project, and in particular, Nicola Corporato and Rob Sokol. Thank you very much.
Thank you so much, Matteo. That was really fascinating, and something that I know, your paper definitely put on many people's radar, as you say, the potential nitrogen implications of decarbonization. And I know I'm currently involved with, and there are several people on this webinar as well, involved in a global N2O assessment, which is going to be coming out later this year. And there have been many discussions about, better understanding the risks, the opportunities, but also the risks associated with these, some of these decarbonization strategies, notably green ammonia. So thank you for that. So our final speaker today is Dr. Sarah Garvey, who's the project manager, or the program manager for the NICCEE Center, and she will be, I will not say that acronym again. She will walk us through that. And then the project director, Zhang, will also be available for the Q&A as we get into a bit more detail on some of the questions. So Sarah, thank you so much, and the floor is yours.
Thank you so much. You should be able to see my slides, I hope.
Yes,
thank you so much for that. Great. Thank you so much for that introduction, as well as Matteo and Trevor. That was really interesting. I'm thrilled to be following up, really sharing something that's a little bit different than what we heard from the previous two speakers. As David said, my name is Sarah. I'm the program manager for the Global Nitrogen Innovation Center for Clean Energy and the Environment. Definitely a mouthful. That's why we go by NICCEE instead. So I'm going to share just a little bit about who we are as a research collective and how we're approaching these issues, how we're thinking about green ammonia, and how we're thinking about bringing down nitrogen waste. So just a little bit about who we are at NICCEE. We're a global research initiative that's dedicated to advancing sustainable nitrogen management. And in order to do that, we're trying to support socioeconomic and technological innovation through use-inspired and data-driven approaches. So I'll talk a little bit more about what I mean by that kind of jargon of use-inspired science. But before I get into that, I just want to emphasize that our initial focus, we just got our funding in January, so we're a really new group, but our initial focus is this emerging technology of green ammonia. And so this photo that I'm showing you here is just some of our NICCEE community at our last in-person meeting. And I also want to acknowledge our director, Dr. Zhang, from the University of Maryland Center for Environmental Science. She's in China right now, so I am stepping in to share this presentation, but she is online, and she'll be joining us for the panel discussion and for the Q&A. So just to talk a little bit about who we are when we're doing this kind of work, trying to support nitrogen innovation, we're a transdisciplinary and transnational network. So that means that we are comprised of folks from all over the world. We have more than 25 different partners in 8 different countries, and we're continuing to grow. And very importantly, we have folks from all different sectors. So we're not just limited to the lab in the classroom. We're not just limited to traditional academic research, but we're also working with the potential users of these research products. And so I really appreciate Matteo's final bullet point calling for a collaborative approach to these conversations. This collaborative approach that we're trying to do by working with the users of our research products is what we're trying to call use-inspired science. So just to give you a little bit of a background, I know I'm the last one to go, so we've already heard a lot about green ammonia, but some of how we are thinking about things here at NICCEE is that nitrogen, we're really faced often with a paradox of too much yet too little, where we've got so much nitrogen loaded into the environment, but there's often too little nitrogen that's available for those that need it. And so what I'm showing you here is I'm showing you a nitrogen fueled algal bloom, and I'm contrasting that with a map of food insecurity from the FAO, as well as showing you what nitrogen deficiency in crops, namely corn, can look like. And so humans are adding about 190 teragrams of nitrogen to the environment annually. I'm not sure if we've got any non-scientists on this call, but 1 teragram is 1 billion kilograms, and a kilogram is about 2.2 pounds. So that is a huge amount. But only 16% of that, about 30 teragrams of nitrogen, was actually consumed by humans as food. So that's a really small portion. And as we've previously said, much of that unused nitrogen is lost in the environment and can lead to environmental issues like local water and air pollution and global issues like climate change and ozone depletion. And so I think this is really, the crux of why we're all gathered here today for today's panel, thinking about what can we do about this nitrogen waste? Where does it come from, and what kind of ways forward do we have? And so, I know that this room is probably pretty biased, but we can consider nitrogen to be at the center of so many different sustainability challenges, food security, agricultural sustainability, renewable energy. And some of these problems require more nitrogen, and some of them require less. And so as we've been talking about, nitrogen is at the center of the new developing technology of green ammonia, which is quite exciting. It can potentially be used for fertilizer and for fuel. We're making ammonia without carbon emissions. And so we at NICCEE are a research initiative of all these different folks from different sectors trying to do science in real time, responding to this new technology. And as I said earlier, this was our initial focus. It's trying to enable and accelerate not only technological innovation, but socioeconomic innovation as well in the face of all of these changes. And so just to kind of like wrap up these final thoughts on green ammonia before I transition into talking a little bit more about NICCEE and how we think about how we approach these kinds of conversations. I just want to state as a kind of a little bit of a reminder from our previous presentations that these opportunities with green ammonia are quite exciting. Using it in fuel, using it in fertilizer, decentralized fertilizer production so farmers could make their own fertilizer on their own land. It's all quite exciting, but more ammonia available probably means more ammonia being used. And so even though green ammonia could offer this really promising path to decarbonize marine shipping, as we've been talking about, doing so would also likely triple the amount of reactive nitrogen that we are introducing into the biosphere. These more readily green nitrogen products would likely mean more use, more misuse, more overuse of nitrogen. And so we're trying to figure out how we at NICCEE fit into this broader conversation, as well as today's conversation about how we bring down nitrogen waste in general. And so we at NICCEE, we're trying to approach these issues using kind of a three-pronged use-inspired lens. So like I said, we're trying to work with users so that we can expand our fundamental knowledge of these issues, as well as respond to these practical problems. And so our NICCEE team is broken down into 3 different sectors that kind of each have their own sets of goals. So I'll just give a little bit about each of them right now, and then I'll dig into some of the exciting work that each group is doing. So in yellow, we'll start with our information hub. This group is aiming to monitor the life cycle and effects of nitrogen in ag, food, and energy systems. So this is, expanding some of our foundational knowledge. We also have an innovation platform. So this group is aiming to co-develop technology and socioeconomic solutions with our stakeholders. So we're working with users to collaborate and co-develop solutions. And our third prong to our approach is our education program. So we're trying to nurture the next generation of scientists and innovators to champion sustainable and climate smart nitrogen management. So these are kind of our 3 different groups, and now we'll take a little bit of a dive into each of them to talk about the different kind of projects that are going on within each across our different collaborators. So I'll start with the information hub. So this one is the goal is to monitor the life cycle and effects of nitrogen in these ag, food, and energy systems. So one of the things that we're doing is developing an open data platform for nitrogen flows in these systems. And this work is actually underway right now. So if you think that you might be interested in contributing data to or using this platform, I do hope that you will get in touch. This visualization that I'm showing you here is showing the suite of methods that we can use to acquire data about nitrogen so that we can populate our nitrogen budgets. And so in order to cut down our waste and be confident about how much waste there is and how much we're cutting, we need accurate data and accurate quantifications of these budgets. So that's kind of part of where this work comes into play. We're also developing farm level and regional level models to assess the impacts and feasibility of innovative tech like green ammonia. And we want to be able to use these tools to assist in decision making for stakeholders, from farmers to policymakers. So we're trying to make things that are usable to the people that actually want to use them in the world. We have a lot of other projects underway within this group. I'm just going to show you a snapshot of a few to pique your interest. This is a map of global nitrogen usage. We're also developing a nitrogen budget to investigate how nitrogen flows through agriculture. We're working alongside stakeholders to develop interactive decision-making tools, as I said, and not shown here, but we also have some colleagues that are working on global change assessment models to simulate the impacts of green ammonia use on the shipping industry. Our innovation platform, to transition to the next one, our innovation platform is about the co-development of technology and socioeconomic solutions with stakeholders. So we've been doing a couple of different things within this sector, and I'm quite excited to share them with you, especially because I have photos to put with this one, always fun. So I'm going to start by talking about our Green Ammonia Technology Advisory Committee. So we were really fortunate enough to be able to assemble a panel of experts to serve in an advisory role for our NICCEE community. And this group is intended to provide some critical insight about the future of green ammonia technology and help shape the direction of our research and our initiatives. And so one of the things that they're doing is developing a 30-year blueprint or a roadmap for what the future of green ammonia technology might look like. And so just to shout them out, this group is led by Nick Wu and Mario Tenuta, and they're joined by Francis Houle, David Zeisel, and Tom Haman, and we are absolutely thrilled to have them on board. Our innovation platform is also using what we're calling a living lab approach. So we are doing research directly on farms in Canada, as well as starting up in the UK. And so this visual I'm showing you here is a green ammonia system in Manitoba, Canada, that was actually just installed on a farm a little more than 1 month ago. And we are collaborating with these folks on this farm in order to do research here about what the effects are going to be on the larger environment. And so we're very, very excited about being able to collaborate again with the actual users. We're also putting together national and regional stakeholder workshops. So we actually recently hosted a regional co-production workshop with more than 15 local farmers in Maryland. That's where I'm based, in Maryland, in the US. So we did that back in March, and we were able to coordinate and collaborate directly with these farmers using the nitrogen products and ask them, what do they want from their environment, what's working and what's not, and what are they excited about for green ammonia, and perhaps even more importantly, what are they cautious about with green ammonia? What are the things that are giving them pause? The last thing that I want to highlight under our innovation platform is our Nitrogen Summer Institute. So this just happened last month. We had our first in-person gathering for our larger NICCEE community. We brought together more than 50 people from all over the world. We went to a local farm to see how things were going there. And then we had 2 days of talks, working groups, and collaborative work. So it was a really, really great experience. Some highlights: we heard from green ammonia production efforts around the world. And I heard lots of different things come from our community: calls for needs for more data, needs for more orchestrated conversation among collaborators and scientists across the green ammonia and nitrogen management realm. Thinking about what kinds of international collaboration will be needed for policy and regulation, as well as what kinds of training we want to pass on to our next generation of scientists. And so this is an annual event, actually. This was just our first one that we just had last month. And some of the great folks here at the INI are also NICCEE community members. We were lucky enough to have them join us in June. And we would love to see more friendly faces next year. So I'll share my contact information again at the end, but we would love to continue to grow our NICCEE community. So please do get in touch. The last point that I want to touch on before I wrap up here is our final sector, which is our education program, trying to foster the next generation of scientists to be champions of sustainable nitrogen management. And so part of how we're doing this is we are developing a graduate level course that we're calling an issue study group. And this issue study group is going to be a course offered across multiple institutions worldwide virtually, so they'll be able to meet up in real time. And students are going to get to learn about these emerging nitrogen-related issues and gain global perspectives. And then we'll be bringing some of these students back to our Nitrogen Summer Institute next year. And we're also trying to connect students with real-world internship opportunities, like at the Nature Conservancy or at FAO. And so we're really trying to use education as a way forward as we think about things like nitrogen management and nitrogen waste. We're trying to educate the next generation of scientists in this really cool, but really, really important area of science. And we're hoping that maybe we can even inspire them to pursue a career that will benefit the long-term, sustainability and development of nitrogen management and ag production. We can dream, we can hope, and we're very excited about where this program is going to go. With that, I will wrap it up and say thank you so much. If you are interested in getting involved with NICCEE, as I said, please do reach out to me. I have my email as well as Shin's email there, and we really look forward to hearing from you. Thanks.
Thank you so much, Sarah. That was a great presentation and overview of NICCEE and the opportunities and kind of the directions in which it's going. So the way that I want to do it, I have a question for each of the presenters, and then I want to open it up. And I see, thank you so much already for engaging in the Q&A, and to the speakers already for answering many of those questions. That's really great and helpful. And as I ask some of these questions, please feel free to continue asking in the Q&A. So my first question is for Trevor, which is, you mentioned how you felt that before even getting to the environmental implications of ammonia, that the health implications would mean that there would have to be very tight controls on ammonia leakage, right? And this is going to reveal my lack of knowledge in this area, but to what extent do the technologies or measures that may limit ammonia leakage? Obviously, the problem with N2O, for example, is when the ammonia is combusted. But I'm wondering, to what extent do the measures that could prevent ammonia leakage also have an effect on the kind of the conversion rate to N2O, if that makes sense? I mean, I imagine in one sense, they're completely separate things. But on the other hand, do some of the measures, to simplify it, do some of the measures that could be taken to avoid the health risks associated with ammonia also improve its potential environmental performance?
So I think your instinct is right that these are broadly separate. The impacts of combustion and conversion are not the same as sort of fugitive emissions across the supply chain. Mm-hmm. But there is a technology suite of gas detection, the ways you contain gases, that is applicable to both. So while you're not going to get N2O emissions from a storage tank or a pipeline, but you are going to get NH3 emissions from a turbine. So you're going to be measuring the NH3 in both the fugitive leaks and in the combustion outcomes. So there's certainly correlation between the technology sets required. I think the combustion ones is very interesting because you've got those three separate species that you really need to be looking at: N2O, NOx, and NH3. And I completely agree with the way Matteo's breaking down the challenge. Probably the biggest task in hand this decade is getting global regulations around N2O, because they don't exist. We got clarity around NOx. There is at least a blueprint around NH3 In Japan, which is the big sort of like early green ammonia import destination, they have extraordinarily strict limits on NH3 because of its smell. Not even because of its health and safety, because they don't like the smell. So there's established around Japanese municipalities really strict limits around ammonia emissions that are stricter than the health and safety ones. Because you smell it at 5 p.m. and you're beginning to worry about the health impacts over a prolonged period of time at around 30 ppm. So at least we have a blueprint, but for N2O, it's definitely going to be a more complex challenge to develop that control. We do have the technology suite. We've figured out how to solve N2O emissions in the nitric acid industry. Now we need to take that catalysis, that technology, and package it in a different system so that it's on board a container ship. And that's definitely a challenge, and we don't have the regulations in place to mandate it, but they're currently under development. The IMO is working hard at that stuff, and we should have some of those. I believe we're going to have some of those coming out of the IMO, International Maritime Organization, in September. So I think we're starting there, but yeah.
Thank you. That was really informative. I appreciate that. Matteo, you know, that figure you showed that I think many of us have seen of kind of essentially the sensitivity analysis showing what the carbon footprint of green and blue ammonia could look like depending on the N2O conversion rate. Do you have a sense already now, you know, Trevor showed obviously the planned capacity expansion, you know, essentially doubling the amount of ammonia that we produce today. Do you have a sense already of what that conversion rate is right now in that range of 0 to 1% of the current production technologies? Do you have a sense of where in the range it is, or is it really kind of dependent from facility to facility?
All right. Well, I'll start by saying that plot that shows the greenhouse gas footprint of ammonia combustion. So it's really relating about the idea of burning ammonia. And this is not done at scale yet. And it's not a problem that will happen in production facilities or, as Trevor mentioned before, in storage tanks or in pipelines. We are really talking where ammonia is burned. Now, that said, there are many numerical studies, especially in the literature, investigating sort of like steady state conditions for ammonia combustion. So numerical simulation that allow the ammonia to completely burn. And in those cases, N2O emissions are low. Okay, so in the sensitivity I showed are in the first part. But this only tells a part of the story because basically the problem here is that ammonia is a kinetic problem. N2O formation is a kinetic problem. There is a lot of N2O formed in the combustion region, and really its emission depend on basically inefficiency of the combustion process. And this is why I also replied in the chat what the combustion experts say. Clearly, again, I'm an environmental engineer, not a combustion expert, is that we need to redesign the combustion engine. First of all, to address the issue of NOx, because they are too high for current regulations, but also for N2O.
Thank you very much, Matteo. You know, we've spent, you know, much of the focus here has been on industrial level production of green ammonia, but one of the key focuses of the NICCEE project are some of these companies that are actually focusing on farm level production of green ammonia, which if it spreads out at a broad scale, could completely upend how the global fertilizer industry, how we produce ammonia, who the big players are, the exposure of farmers to variations in fertilizer prices due to various geopolitical crises. And so Sarah and Shin, you know, this is one of the real innovations of NICCEE, is looking at the farm level production of green ammonia. And obviously it's very difficult to know how big it could become, but if you could just speak to what NICCEE is doing on that front and some of the both the challenges and opportunities that you're seeing so far. I know there have already been some regional workshops exploring it, and you're partnering with some of the startups that are really pioneering this. So if you could speak to that.
Yeah, I'm happy to share a little bit, but I think we're fortunate enough to have Shin on this call, and we haven't gotten to hear from her yet. Shin, would you like to share a little bit and maybe say hi?
Yeah, thank you, Sarah, for stepping in for the presentation. I'm just a little bit worried the internet may not be very stable for me to present at some point. Yes, so the challenges and opportunities for the green ammonia usage on the farm level. So as you have seen from Sarah's presentation, that there's already some distributed unit of green ammonia productions facilities that being set up on along the side of the farms, and they are starting to testing the production and also its applications in the farms. That's one side in Canada, and there's another company that doing some work in Kenya, and there may be another its facility is setting up in the US. So it's happening. Meanwhile, we're trying to as Sarah mentioned, we have this workshop earlier in the Chesapeake Bay region, trying to understand for farmers to adopt such type of technologies. What are the incentives and barriers? And one thing interesting to hear from the farmers is that so this type of distributed units are potentially attractive for them, particularly in the current context of a rather volatile fertilizer price, and by having enabling the capability of producing ammonia on their site, which is a major input for the farms, is a good or provide some competitive advantage for them. But on the other hand, it's kind of similar to the application in the energy or shipping sectors. The safety issue is one major concern, and also maybe some legal barriers for bringing the ammonia production units on the farms. And another practical issue that we see during our past interactions is that the current green ammonia production units, like the distributed units, are mostly producing the anhydrous ammonia or aqueous ammonia, which is not the typical fertilizer types that being used widely in many parts of the world. Some parts of Canada and US are using anhydrous ammonia, but it's not currently used everywhere. So that's kind of the one challenge of bridging the gaps between the needs by the end users and what is the current the industrial innovations are taking place. So that's one thing that we're very excited that we're getting these opportunities to serve as a platform to kind of further better understand those the gaps and provide some options to match the needs with the innovation that is currently ongoing. I'm not intending to cover all of the challenges, but I think those are some of the major ones that currently are on the top of our mind.
Thank you so much, Shin. So we have about 15 minutes left, and I've noticed, again, some great questions in Q&A, and I wanted to hand over to the INI Operations Manager, Edin Thornton, who has been closely monitoring the Q&A chat and is going to try and distill some or aggregate some questions together where possible to ask our panelists some of those, to get responses to some of those questions.
Thank you, David. Hello, everyone. I wanted to thank our panelists for their contributions so far. And my first question to everyone, and anyone can jump in where you would like, would be, what do you think the most common misconceptions about green ammonia are that you encounter in your work?
Well, I'm always happy to start. So I think people think green ammonia is like this silver bullet, if only we can get there. And so, you know, Jin's just brought up a really important point. People don't actually use ammonia as a fertilizer. Like, this isn't like, oh, I can just take out the carbon dioxide and all of a sudden I've decarbonized agriculture. Well, first of all, we use urea, which you make by combining ammonia with the carbon dioxide that you just split to make the ammonia in the first place. So your industrial ammonia plants are using their emissions, not all of them, to make a product that then emits all that carbon dioxide back into the atmosphere. But even that's only a small part of the footprint of the agricultural. Then you've got all the on-field N2O. And so if you were decarbonizing your ammonia plants, that's going to take perhaps 15 to 30% of your fertilizer carbon footprint. Then when you actually get to the application of that fertilizer, you've got all the rest of the emissions. So just green ammonia doesn't solve out agriculture. Certainly, you can get rid of 1% of global emissions, but the agricultural impact is much greater than 1%. So that, I think that would probably be the starting point. The other thing is there's green, there's blue, there's a lot of different flavors of technology pathways that you can be making ammonia with. I'm not a big fan of colors. We have got different definitions of green in the EU versus what we have in South Korea versus what we have in the US. What does green mean? Does that mean we have new build direct connection renewables facilities? Or does it mean we're plugged into a grid with a PPA, but mainly it's just local coal? It's massively important that we have the carbon accounting in place. At the Ammonia Energy Association, we're developing a certification system for measuring the absolute emissions associated with the ton of ammonia. Getting that, whether it's green, blue, pink, yellow, it doesn't matter. We should be able to count the emissions. We might also care whether it's green or blue, but we need to be able to count the emissions. And so moving beyond that sort of easy label, green is good, blue, we may have an opinion about, gray is bad. Actually being able to say, well, this ton of ammonia has a carbon footprint of 0.015 tons CO2e per ton NH3, and therefore it has this a value attached to it because of its carbon footprint. That's where we want to get to.
Thank you. I'm not sure if anybody else wanted to answer. Thanks, Matteo.
Yeah, I'll just follow up. Something that Willie had already said a couple more times, but I repeat myself. One thing I've often encountered when speaking about green ammonia with also the energy sector is, look, the ammonia molecule, NH3, there is no carbon, hence we are fine. And clearly that's not the case. It's the case only if things are really done properly. Ammonia itself and NOx that are not direct greenhouse gas have a climatic impact, whether emitted to the atmosphere. And then there is really N2O, that when we're talking about climate change mitigation is the elephant in the room.
Just to add just a little bit extra, thank you both for those comments. Trevor's comments kind of make me think just more broadly as someone that is working more in the user space and trying to speak with people like farmers and things. Something that I find comes up a lot in my conversations is the way that buzzwords associated with green ammonia can come off as, oh, that's perfect, kind of like Trevor was saying, of a silver bullet. But if you're not careful when you're presenting this information about providing the appropriate nuance about the larger system implications, that it can be quite easy to just say, oh, green ammonia, decarbonize, end of conversation. And that is not the most useful. The other thing that it makes me think of is a lack of standardized jargon. I hear what you're saying about the color thing and about these words not necessarily being very meaningful, but there's also kind of nuance within them. You know, green ammonia can mean a couple of different things. How do you produce that green ammonia? There are different ways to make it, and how do we talk about it? Because right now, as far as I'm aware, people kind of talk about it in lots of different ways, and there's a lack of standardized words here, and that prevents us from being able to bring together our science more effectively because we're all speaking differently. So the more that we're able to have these kinds of conversations where we can all get together and kind of get on the same page, I think the better that will go.
Maybe I just add quickly about the green ammonia concept. During our the meetings last week, we had this not last month, we had this debates about what exactly is green ammonia from this green ammonia technology advisory group. And a lot of the green ammonia technology that was discussed earlier and also being more widely, used right now is essentially producing the ammonia with still with a Haber-Bosch process, but just using the renewable energies. But there are also other types of green ammonia technologies that can that are being developed to avoid, to produce ammonia without using this high pressure, high temperature Haber-Bosch process. And those technologies are currently in the kind of development and also can have provide some more benefits to the broader decarbonization tools.
If I might just add on to what Jin's saying there, there's one additional sort of misconception, I think, which is that all nitrogen fertilizers begin with ammonia. And if we go back 100 years before we had Haber-Bosch, we had the electric arc. The electric arc process made nitrates. It didn't make ammonia. It's essentially making NOx. So that, in fact, while some of the technologies that Zhang and Sarah are working on are working with are moving directly to ammonia, you've got a lot of potential for electrochemical technologies that are skipping ammonia and going straight to the nitrates. So that then is addressing directly the decarbonization of fertilizers in a localized way. And I think that's a very exciting technology suite that we're seeing being commercialized right now.
Thank you, Trevor. Those were all very insightful answers. And I'm interested, we've got about 5 minutes left, so I'm going to lump together a couple of questions here, and you may feel free to answer whichever one you feel like best suits you. So there was a really interesting question here in the Q&A section from Dr. Mark Sutton, noting that the European Space Agency has failed to fund the NitroSat project, which I will right now send a link to everyone in the webinar in the chat. It was intended to be a dedicated satellite monitoring tool for nitrogen, specifically ammonia and nitrous oxide. And so in this vein, so the question is, what ideas do the panelists have for how to mobilize the urgency of funding for a high resolution satellite project? I've also heard through the discussion that there's a general lack of funding for green ammonia technologies. And I'm curious what the panelists think is the best way to mobilize funding, and also interest from policymakers, as well as our industry actors who we've been talking about.
Yeah, I think I add a few points in the chat to Mark's questions, but yeah, maybe so yeah, mostly yeah, from my point of view, what we can do currently is trying to get the better communications with the potential impacts, and then trying to have highlight the need for monitoring the impacts. And also, I have when I listened to what Trevor was presenting, there's one question in the back of my mind that for the current industrial partners that using working on using ammonia as energy, whether there's certain incentives or motivations to support some of those monitoring approaches to kind of make sure everyone is a good actors. So I didn't mean to put you on the spot, but just kind of trying to see whether in this case, whether the private sector and the public sector can potentially join force and support those type of monitoring approaches so we can effectively monitoring the impact.
Well, if I can, I'm going to add on to that. You know, in Matteo's presentation, we had that satellite imagery, and that's the Donaldsonville plant in Louisiana that I actually visited 2 weeks ago. And I can promise you, you can't smell the ammonia. So if you're walking around there, it's less than 5 ppm. But so that's the world's possibly the best operational producer of ammonia on the planet. They know exactly how to do it. They have a tremendous health and safety protocol. They have a lot of reporting requirements to the EPA. They have they know how to produce ammonia really, 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 really well. Now imagine we're expanding this around the world, and all of a sudden we've got 10 million ton per year ammonia plants being built in Namibia, in Mauritania, in Kazakhstan. Now, what are the regulations in those economies? What is the monitoring? What's the health and safety regime there? Can we like, you guys are jumping on industry, and I'm like, well, okay, but they kind of do it the best we can do it today. Now I'm worried about all the other people that are going to be beginning this journey. Do we have the health and safety personnel? Do we have the health and safety protocols? Do we have the regulations in place? Do we know how to follow the regulations? Can we afford the technology suite? Because health and safety is expensive. And so we have to get this right. We have to do it properly. And I think we have the challenges in focus. We just have to make sure that we step up and meet them.
So we are at time now. It is 3:30, and the last thing I want to do is to cut into people's lunch, breakfast, bedtime, dinner, snack, drink. But I do want to take a moment just to give a deep thanks to Trevor, to Matteo, Sarah, and Shin for such thoughtful and insightful presentations and answers to questions. These webinars are only ever as good as the panelists and their commitment to them, and this one was really a great one of my favorites so far. So I really appreciate your time and effort on this. These webinars are roughly once every quarter, and they are organized around this general theme of halving nitrogen waste, halving nitrogen losses to the environment. And we are very much open to ideas for what kinds of topics we should be covering in these webinars, and the kinds of people, both not just academics, but people from, you know, across a whole range of stakeholders should be involved. So please reach out to me, reach out to Edin. Her email is operations@initrogen.org with any ideas for things that we should be focusing on in these webinars. And with that, thank you so much. And please be on the lookout for future webinars and other events and things coming from INI. Thank you all very much. And thank you to the panelists again. Take care.